Okay, welcome everybody to the webinar today. I appreciate your attendance and the opportunity to share some things we've been up to at Coreform. I'm joined today by Greg Vernon, who's our leads our product development team at Coreform. He's going to also present during part of the webinar. I'm going to be the presenter. My name is Mike Scott. I'm the CEO of Coreform. And at Coreform, we're striving to improve the engineering design process in general, focusing on numerical methods like the finite element method and improving workflow and automation capabilities. So today we'll just give a little bit of an overview about the company for those of you that are just joining us for the first time and would like to know more about what we're about. I'll talk a little bit about our flagship product called Coreform Flex. I'll then do a dive into describing kind of the key value proposition and how we improve the engineering design process. And I'll give a few examples that demonstrate the power of the method and help lay the foundation for the demo that Greg Vernon will then give. At the end of that, we'll have a period of question and answers, and that will bring the webinar to a close. So Coreform was founded in 2014. We're in the state of Utah, a little south of Salt Lake City in the Mountain West. And the company kind of started in my research lab and then grew, and we moved it off campus and have since been working on kind of a commercial centered activities. The foundation, I would say, like the scientific or technical foundation of what we do at Coreform, started in the field of isogeometric analysis, which is a generalization of finite element analysis that overcomes the bottlenecks associated with meshing and CAD cleanup by striving to incorporate the exact CAD design definition directly into the finite element analysis procedure. And this provides a number of advantages, including obviously automation, workflow advantages, because it eliminates time-consuming aspects of the process. And it also provides superior simulation results in the context of both accuracy and robustness for dynamic and nonlinear types of simulations. So Coreform Flex is a product that we're just introducing to the market. That's one of the purposes of the webinar, is to get the word out that this is now available for testing and for purchase. And it's the first solver built natively on top of this new isogeometric analysis technology. And it enables a fully automatable mesh-based workflow. And I'll show these examples, a couple of examples to illustrate the approach in a moment. We use kind of a generalization of the isogeometric methodology to be able to operate on the simulation models that we produce. We call that method the flex representation method. It likewise is a type of finite element method. So this isn't kind of I would say, some novel or niche approach. We're using a standard finite element approach based on, if you're familiar, if you have kind of a deeper understanding of finite elements, it still uses the standard Galerkin approach. And another really great thing about it is because the technology is a generalization of finite elements, it can support any capability that's also available in a more traditional finite element workflow. So it doesn't require that you discard the years of work that had been put into the development of workflows around traditional simulation packages. So, like I said, we're introducing this new product, Coreform Flex, and we are rolling it out, I would say, conservatively to make sure that we're addressing customer needs. So we like to work directly with people that are interested to make sure it's fit for purpose, make sure that we have capabilities that would benefit our customers, and to give them an understanding of our roadmap so that they can incorporate this efficiently and in a way that makes sure that we respect their time and their resources. So, as is the case with most new finite element capabilities, the most robust capability is linear elastostatics, but we're very close to releasing, moving out of beta, a full nonlinear structural mechanics capability that includes contact as well. So that's kind of where we're at, and I'll talk a little bit more about this at the beginning, or at the end. We'll encourage you to reach out and give it a shot to try it yourself. Okay, so let's go ahead and talk a little bit about the traditional finite element approach to model setup, which is one of the most time-consuming parts of the process. And it's unfortunate because it really doesn't add value in the sense that it does not really provide any engineering insight, which is the point of running a simulation. It's really just an activity to try and massage CAD data into a format that's consumable by a finite element type algorithm. And so here's an example where we use a kind of a traditional workflow to put a hex mesh onto this CAD geometry. And what you'll see is, and what we're demonstrating here is just the huge number of steps, including a number of defeaturing steps to allow us to then cut up the geometry into hex meshable subvolumes. Tet meshing, of course, is a little more automated, but it still often requires a defeaturing step and is not completely robust. And what we're really after at Coreform is, given any CAD geometry, can we exactly generate a representation that's consumable by a solver that is an exact representation of the original CAD at any level of complexity that the user would desire. Okay, and so this takes a long time to do. We had an expert user do this. In fact, it was Greg Vernon that did this, and he's done this model a number of times. So he was able to do it, I think, in about 20 to 30 minutes. But if he was to do this for the first time and he hadn't seen the geometry before, he estimates that this process would take about 20 hours to do. So that just, the intent there is just to give an overview to people that may not be as familiar with the pain that's felt when people are really trying to prep models for simulation. This isn't even about, running the simulation. And then often the mesh that you produce may not be sufficient for the simulation, which then puts you in this position where you have to go back and remesh, change your approach. It just becomes very, very challenging. And it's just a waste of time and resources. Okay, so let me show you now our approach, which is really powered by the key or core concepts of isogeometric analysis, which says that the CAD geometry is defined in terms of a set of basis functions that can be used in simulation. In fact, those functions are smooth and higher order, which is a really powerful from a numerical analysis point of view. is in some sense the most efficient and powerful type of set of functions that you could use for approximation in finite elements. And what this allows us to do is it allows us to kind of rethink the I would say the process of bringing the CAD model directly into the solve without needing to do what I would call a traditional meshing step. And I'll show you here what we do instead. We do produce a mesh. You know, every finite element method, regardless of how it's marketed or sold, has some type of a discretization or mesh in the background. And we likewise have a mesh, but the process of generating that re-representation of CAD, and I should say that CAD also has a mesh because it's also represented in terms of functions and geometric nodes and so on. The process of us doing that can be fully automated. Let me give you an example so visually you can see what I'm referring to here. So here's the same CAD model that we showed previously, but now we're going to bring it into Coreform Flex and prepare it for simulation. And you'll notice the difference right off of the bat here. Okay, so we bring the model in, and the meshing process really is what you would call an immersed technique, which puts a higher order smooth spline background grid. It overlays it over the geometry and then produces and then runs a automated trimming procedure to generate a volumetric CAD object that is an exact representation of the original CAD object. And so that's the entire model prep process. Is we just ran it through trimming, and now we have a representation of the interior of the object as well. And the functions that will be used for simulation are the smooth higher order functions that are defined on the rectilinear background grid. So they have beautiful approximation properties that you can leverage. And then you can run the simulation directly on the fully featured CAD. If you desire to remove features, that's fine. I mean, any CAD object that you feed into the trimming procedure will be accommodated automatically. And so here's just a very simple simulation to show that it's computable. Here's a more complex part, just to demonstrate that we can do things that are, if you think about meshing something like this, this can be extremely challenging. I mean, if you want a hex mesh, it's essentially impossible. Even, if you want to mid-surface it for shells, it's very, very challenging. And I think Greg Vernon can correct me if I'm wrong, but we weren't even able to tet mesh this object because the geometry was quote unquote dirty. So
that's correct.
So in fact, this model could not be meshed by any known meshing process that we have available to us. And let me show you the process with our approach. Well, what you'll notice is there was no process, right? So we just trimmed the model, and what you're seeing on the screen is the result of trimming. It's an exact representation of the geometry, but it's a volumetric model. So it's not just a collection of bounding surfaces like the original solid CAD model. It's actually a high fidelity simulation model that you can simulate on directly. And so then we just applied a load on the interior, a pressurization, just to demonstrate that the model is computable, of high quality. Likewise, this particular model is an assembly of parts. So there's the top and bottom pieces, and the screws are actually modeled with tied contact, mechanical contact. There's contact between this upper part and the lower part. So it's actually an assembly of parts that are being held together as it would be held together in its physical instantiation. All right. And just to, I would say, emphasize that point, here is the same problem, but now we've highlighted the different parts of this assembly. And I always get a kick out of how even the embossings, we capture the embossings. I mean, of course, you could get rid of them if you didn't, if they weren't of any engineering relevance. But it's great to have a method that can preserve as much or as little of the CAD exactness as the user wants. You're not forced into a position where you're defeaturing just for the sake of, can I get a mesh on it so that I can actually run a simulation? Our users have full flexibility and can make those decisions based on the best practices and engineering judgment that they bring to the problem. Here's another example. Again, just some complexity. Here we're showing a contact problem. So this is a highly nonlinear dynamic. This is an explicit dynamic simulation with contact. And so we have, like I mentioned at the beginning, these are the features that will be released soon. And so you can see that, contact is also quite robust because it operates on this nice smooth geometry, which is a big deal for contact. If you have a background in contact, you'll know that the faceting is a challenge with contact. You're kind of especially sliding contact across faceted surfaces can produce a lot of numerical noise. And since we're operating on the exact geometry, we don't suffer from those challenges, which makes nonlinear convergence much more robust. Okay. So I'm going to bring to a conclusion my introductory comments about Coreform. Like I say, we will address questions after Greg does his demo, so you can kind of see. I imagine there's questions about the software and like how it works. So hopefully we can answer some of those in the next section that Greg is gonna lead. If you feel like you would like to try this out on problems of interest, please contact us to become an early adopter of Coreform Flex. We're actively moving this into the market, and love to work with people who are in a position to introduce new capabilities into the organizations that they work with or feel like this may bring something of value to their problem. Matt Cedarberg is leading some of those business development efforts, and I've included his email on the last slide for you to reach out to him. So I'll let Greg now give a demo of our software, and then following that, we'll have a period of question and answer. Take it away, Greg.
So I'm going to share my screen real quick for this demo. And this is maybe one that some of you have seen before, but we'll show an additional example as well. What I want to point out is that for any of our early adopters who are using Coreform Flex, we have a few pre-baked examples that come with Coreform Flex, including kind of the standard plate with a hole, as well as this C-frame example. The other example I'll share today is this door lock assembly example. And I just want to get you familiar with the overall workflow of using our tool. You can see we have kind of these two model trees, a geometry model tree, and then our IGA, which stands for isogeometric analysis, our IGA model tree where you specify solver settings. Note that the mesh then is defined on the CAD. And really the process to create the mesh is pretty straightforward. At the top right, we have what we call our mesh manager, which is a little kind of wizard dialog where the process of generating the mesh is as simple as choosing the part I wish to mesh and clicking the little plus button to add a mesh, which picks an automatic size based on some heuristics oftentimes that mesh size is a little coarser than we might wish to have. And so we can choose, we can navigate into this mesh. I want to point out that we currently have what we call primitive meshes, which include like this rectilinear background grid. We're developing additional primitive schemes like a sphere mesh for parts that are mostly spherical, or annulus meshes for parts that are kind of like a torus. But you can even bring in a traditional body fit CAD mesh as well, which really kind of highlights um, the fact that what we're building is actually truly a generalization of finite elements. And within this rectilinear primitive mesh, we can just simply choose a size that we think maybe works better for our case here. So I'm choosing a mesh size of 0.25, for instance, for this case. And maybe that's a mesh now that is fine enough for my purposes. And that's it. Like, meshing from a user standpoint is done. The trimming process will occur automatically when we launch a simulation. I can choose to generate the mesh independent of the simulation if I wish to um, preview it, but that's all I have to worry about. As far as in the rest of the simulation setup goes, what we recommend our users utilize is we call the actual physics solve. We call those a procedure. And so we recommend that users begin by adding a procedure to their model. And you can see here we have a few different physics that we currently support. The modal analysis and heat transfer are still in beta stages. Solid mechanics is what we're talking about today. And then as a user might go through here, maybe I want to choose a time stepping method. We'll bring up a little dialog that assists you with kind of navigating the model tree for adding the physics you wish to add. So you can see we have a few different time steppers, including an explicit dynamic time stepper, some implicit dynamic steppers, a nonlinear static solver, and even linear solvers as well. So if we wanted to do a linear analysis, we could choose I want to do a linear analysis, and that linear analysis needs a linear equation solver. And again, I can navigate this little breadcrumb interface to choose I want to direct an LU decomposition based solver. And then as I finish each step, you'll notice that there have been these stop signs along the way, and the stop signs for this sub procedure have gone away. And I would essentially just navigate my way through this procedure tree, adding a time interval for my model, creating a flex model, where I would say I want this C-frame part to be active in my assembly. I want to add a material for my model. And again, navigating through the model tree here. But then as far as actually, I'll just put in some dummy values here just so we don't get some syntax errors. As far as then actually running the simulation, we then have a job manager as well, where we would say, add a job, and I wanted to run a simulation, and I would choose the amount of cores that I would want to run on, and then I would just simply submit my job. And that's really the process of the workflow now. Everything, because meshing is gone from the workflow as far as a manual iterative process, it's really quick to just set up the simulation parameters and execute. I want to also mention that all of these commands that I've been clicking through in the model tree have been issuing what we call flex commands. These are strings of commands that you could add to a journal file and automatically play. But furthermore, any of these commands, we support Python wrapping around those commands. So we ship what we call our Flex Python API. Here in the command module, I'm just going to shebang over to a Python interface. Any of these commands, I can simply reference the Flex module and then use the CMD or command function. And I can say that I want to submit, I want to create a new job. So I'm just going to copy the syntax that I saw here to then create a new job. And so this allows you to even import Flex as a Python module into an external Python. So for those of you who care about scripting and automation, especially in this day and age of AI, you now have a completely robust meshing interface that can be then fully automated via Python. And so Flex can operate right next to your PyTorch, for instance. This is a single assembly. And I just want to now show a more complex assembly. This other example that we provide, the door lock assembly, and we'll see that the workflow is essentially the exact same here, where the first process that I'm going to do here, you can see I've got my 3 parts, is I'm just going to add meshes to each one individually. So I'll add a mesh to part 1. That is this door, or this link here. It kind of is wavy. And again, I'll choose a mesh size. Maybe I'll choose a mesh size of 3 by 3 by 3. Yeah, those could be non-uniform values if I wished. So I'm done meshing the link now. So I'll go ahead and hide that mesh. So now I'll add a mesh to the second part, which is this hinge on the back side. And again, I'll modify its element size to something that's more reasonable for my analysis. Okay, so now I'm done meshing that part. And now I'll mesh the bolt. And again, choosing a mesh size, I'll just choose that same mesh size of 3 by 3 by 3. So there you have it. I am now done meshing this assembly. It didn't matter that there were 3 parts. It didn't matter that these parts are, some of these parts are kind of maybe thin structures or sheet metal, like bent sheet metal structures. The meshing process is the exact same. Some of you may be aware that this is also an example that we have documented on our forums with a traditional meshing software called Qubit. And it's a quite involved process to build a hex mesh with traditional meshing processes. It's probably about, for an expert user, about 15 minutes to build a mesh. For a novice user, it's maybe a couple hours to try to build a hex mesh on this assembly. And from here, I just go on and I would just do the exact same process of creating a procedure, get another solid mechanics procedure. Maybe this time I'll just show assigning a couple boundary conditions. So in this case, I want to hold the bottom of this link fixed. So I'll just create a boundary condition. That's going to be a displacement boundary condition. And I'm going to completely constrain it in the X, Y, and Z directions. And I want it to not move at all. So I'll choose that I want it to move by 0. I'll create a time-dependent function that is just a constant value that can be scaled by time. And so I chose 1 and then scaled it to 0. The one important thing now is I just need to create a set. So I'll just click a plus by the set that I want to apply this onto, and then use the set manager to then quickly choose the surfaces that I want involved in that set. And I want to point out, as I've chosen the sets after I've already built the mesh. And so if you're familiar with CAD-based meshing processes, if I wanted a different region for my set, that maybe I needed to subdivide the surface even further to have a smaller region, you would oftentimes need to remesh and redevelop your meshing routine to build that new body fit hex mesh. But I am completely now separated the set assignment for load and boundary conditions from the meshing process. And so there's no iteration on your mesh just because you want a new set. And that's really it. I mean, we could go through all the rest of this process of choosing, the material models to include plasticity, adding contact, a general contact algorithm, our time steppers. But that's really just a lot of parameter selection at this point, and there's no more meshing at least. And again, this is fully automated. And if you look at the journal files that open up when we run this problem, you can see again that it's been fully automated to make all those selections and then run this analysis.
So Greg, could you, I think you said this, can you, just wanted to emphasize that boundaries and loads are applied directly to the CAD object.
Yes. Yep.
So we don't apply boundary conditions to node sets, for example,
Yep.
or element surfaces. It's all done directly on the CAD object that you've trimmed.
Yep.
Then another question came in about the order of the elements. I think in this case there's C1 quadratic. And,
Yes. Yep.
and so we support currently up to Cortex C3. Um, that's all that we've had a need to do so far. We could go higher order than that, but haven't seen a use case for it yet.
Yep. Yep. That's a great point. And as you can see here, also in the mesh manager, this is where you could specify that degree. By default, we build maximally smooth splines. So for quadratics, that would be a C1. But you could also choose a custom continuity if you wanted. So you could have P2C0 if you wished.
Okay, another question, Greg, is about preloading of the bolts. Are you able to preload the bolt in this example?
Yeah, we don't yet support preloads as a separate routine. We do have user-based, or our user subroutines are based on Julia. And so today, if you wanted to do a bolt preload, you would have to define a custom Julia subroutine that would apply internal forces or displacements to achieve the bolt preload. That is something that we're looking to add. As Mike mentioned, we have this initial beta capability of having this solver. And then these things about having like bolt preloads are really implementation details that we're looking for feedback from our users as far as what features they would like to have and how they'd like to interact with those kind of with those features.
So a question that comes in, can you show us what a trimmed part mesh looks like?
Yeah, we can certainly do that. Let's go back to the C-frame example here. And let me just double check my mesh for this. Yeah, so let's go ahead and I'll just perform just a trim job on this part. So I'm going to trim this. Should also mention that the trimming process is a parallel process. So traditional hex meshing and tap meshing are traditionally serial or single core processes, but we've developed this algorithm to be parallelized. So I'm just going to launch this trim job. And I'm just looking at the output from this job here. So you can see it finished trimming that part in about 6.5 seconds. And then I'm going to visualize the trim mesh. I want to point out what you're going to see is for the rendering inside of Coreform Flex, we produce just a linear faceting of the high order underlying geometry. So it's going to look a little faceted, like almost like an STL file. But just know that the actual representation is the CAD. So I'm going to hide the actual CAD body now. So then what you can see here are the black lines are the CAD entities. So we're able to understand where the original CAD features are in this trimmed mesh. And then these red lines or pink lines are the boundaries of those trimmed elements. And so that's what the trimmed mesh looks like in this case.
Okay. Thanks, Greg. Another question comes in, any dependencies of Flex on Qubit? I can answer that one. So you can prepare Flex models in Qubit and export them to a file that can then be read into Flex, but we don't embed Qubit inside of Flex. If that's I believe that's the question.
Yeah. And to add to that as well, that Qubit, the inspiration for the Flex Python API came from Qubit. And so Qubit has a very powerful Python API, and it can also be imported into an existing Python session. And so we oftentimes do that in our consulting work here at Coreform, that we use Coreform Qubit and Coreform Flex in fully automated Python scripts um, to run our analyses.
Okay, thanks, Greg. A few more for you, I think, here. Can we assign a custom relation between stress and strain? Also, can we assign different materials for the different parts of our model?
Yeah, we can definitely assign different materials. We do have a limited set of materials today. You can see here our material models that we include. We have a traditional linear Hookean elasticity model that we don't really recommend users use, but it's there for being able to verify to traditional finite element codes that have those elasticity models. We also have large deformation elasticity, a Mooney-Rivlin material. Both the Neo-Hookean and Mooney-Rivlin support near incompressible elasticity formulations. You can see we have a isotropic heat conduction model as well as a Neo-Hookean elasticity with isotropic plasticity on it. Again, we're looking for feedback from our users for additional material models to add, but you can assign unique material models or materials and material models to individual parts of your assembly. As far as the unique relationship between stress and strain, our plan is to use Julia as our user subroutines, as well as not just for assigning custom boundary and load conditions, but also for defining user materials. However, that the user material interface is not yet available in Coreform Flex to external users. And so maybe I'll just at least show where you would access a Julia subroutine. You can see here that there's just another option here from piecewise linear constant. I can choose custom Julia, and then I can point it to the Julia file in a function within that file that's the main calling function, and then choose a return type. So again, as our needs for the Julia subroutines grow, then we'll expand the capabilities of this utility. And I think one of the things that's valuable about this is that if you're familiar with Julia, it is just-in-time compiled. So it's as easy to run in a solve as something like MATLAB or Python. There's no compile step that you have to worry about. So you don't have to worry about making sure you have this compilers on a Windows machine and on a Linux HPC system. Julia will handle all that for you.
Okay, a couple other questions. Okay, so that was the can we assign a custom relation between stress and strain?
Mm-hmm.
It's been answered. What are the key differences between Coreform Suite, Flex, and Qubit? Okay, Coreform Qubit is a traditional mesh and geometry preparation package for FEA. Coreform Flex is entirely this new method that we described today, and Coreform Suite is both of them together, because sometimes you'll want to use Qubit for certain traditional meshing processes and combine them with a Flex model. Okay. Here's another question. Coreform Flex currently uses rectilinear mesh type for the trimming. Is there any plan to add other mesh types beyond rectilinear mesh, like cylindrical and annular cylindrical, and combinations of the different mesh types? Yes, in fact, I'm not sure we've exposed it yet, but we do have cylinders, I believe, already. And you can also actually in Qubit create any type of background mesh that you wish and export it into Flex. It could be body fit, it could be partially body fit. Any and all combinations are currently supported in Flex.
Mhm.
Okay. Can incompressible models, not just nearly incompressible models, be used? We've only explored near incompressibility so far, but since this is a strict generalization of FEA, any mixed method, for example, that you might use to discretize in a purely incompressible model can be developed for our approach, but we have not yet done that. Okay. Have you done any experimental verification? Yeah, just with our customers, for example, they partners that we're working with often have experimental data that they want to that they benchmark both FEA against as well as our tools. And so there's nothing surprising there. It behaves with greater accuracy and robustness than FEA does. So you get more accurate solutions with less degrees of freedom, and in time dependent problems, you get superior discrete spectra that improve conditioning of linear systems in the implicit setting and larger explicit time steps than you would get with traditional FEA in the explicit setting. Okay, can we assign constraint equations between 2 points in a domain? For example, periodic boundary conditions. I do not believe we support that yet, Greg.
Yeah, we don't yet support that. We are aware of desires for stuff like couplings, like kinematic couplings, we do have tie constraints, which is one method of coupling kind of two different regions. As far as like the true periodic boundary conditions, we don't have that yet. And again, I'll just repeat the line that this is the kind of feedback we're looking for from our users for what are the next features to implement in our code.
And let me just segue into another comment that I think is important here, especially considering the number of questions we've kind of got on the interoperability between FEA and IGA. Although we're not yet publicly, like on our website, advertising this, we are deep in an integration of our tools with Abacus, which would allow a user who has an established FEA workflow to seamlessly incorporate these kinds of capabilities within their existing Abacus-based workflows. So that's something that we'll be talking more about in the future as time goes on. So any of these issues where you're wondering, I've got like special, constraint types or connection types that are supported in traditional FEA solvers, all of those you'll get for free, and any part of the model that you want to use FEA on, you'll be able to use, or IGA on, you'll be able to use the trimming procedure and connect it, for example, to traditional beams and shells and connectors and things of that nature. A lot of good questions here. Okay, so we've got that one done.
Mike, I wanted to give at least one addendum to the user who asked about the verification.
Yep.
And so we do have a verification manual that's publicly available at docs.coreform.com. And so we run these verification problems as part of our CI pipelines. So as we make updates to our code, we're always making sure that we're passing these verification problems, and then we generate the documentation directly from those results. So these are the live results of our verification. So if this is something that's interesting to you, you can see that we have some problems for linear stress analysis, large deformation, incompressible or really nearly incompressible elasticity, plasticity, and mechanical contact. And as we finish more verification problems, we publish more and more of them here.
Okay. asking about element death, element activation. We do have an element death capability. We do not have an element activation capability. Can you comment on the runtime comparison with traditional FEA for explicit? How is the critical time set affected by switch? Okay, so let me answer that one. So per degree of freedom, our approaches are more expensive computationally than, for example, I would say nodal linear FEA. But since you have orders of magnitude fewer nodes and the spectra is better behaved, meaning that you get superior conditioning, larger explicit time steps, what we find in general for industrial scale problems that are nonlinear and dynamic, our runtime is superior to traditional FEA. So all of those different features compound since you're in this nested looping structure when you have nonlinearities and dynamics activated in your simulation. Okay. This is another question about material failure. For example, element deletion seems unlikely given the large element sizes. We can actually have what I would call different resolutions within an element. So all the way down from like failure at a quadrature point up through, subdivisions of the large element. We've experimented with several of those. So I hesitate to say more about it because we haven't spent a lot, this hasn't been a real focus. But yes, we do have some basic element failure. And the large element sizes won't be an issue because we have subdivision procedures that can be applied instead.
Mm-hmm.
Okay.
A comment on the large element size as well is, Mike, here I've used like a large element size kind of in a uniform size on each individual entity. Splines support like local adaptivity in them. That's not something that we have today, but we are working on some local adaptivity capabilities.
Yeah, that's right. Yeah, and I answered that in another written answer. And just so the attendees know, I'm going to answer every question. If you've gotten the information that you need, feel free to duck out. But I'm going to stay on until I answer every question. There won't be any new content, though. You're not going to miss any. There's not any more of a presentation. We'll just be doing questions for the remainder of the time.
Yep. And this recording will share out with everyone. So if you do have to leave now and you want to hear the rest of the Q&A session, you'll be able to watch that portion.
A good question. Will implicit and then explicit, or explicit and then implicit be used? So sequential, kind of steps, where you're turning off and on procedures, will that be allowed? We don't currently allow that in Coreform Flex. It is on our roadmap. Part of, the integration that we're making with other more traditional solvers all of that will then come for free, because whatever they can do today, they'll be able to continue to do with our approaches. But
yep. That is our plan, though, is to eventually support multiple procedures and a seamless seamless transition between explicit dynamics to implicit dynamics, or explicit to continuation. And that is a design goal that we have.
Is a similar integration being considered with ANSYS? We have a long standing relationship with LSTC, now a part of ANSYS, so LS-DYNA. I would not be surprised if we did do an integration there at some point, but it's not actively being pursued. So questions about the Abacus integration. Is it both for 3D experience and CAE? We're currently focused on Abacus CAE for that. All right. Can the preprocessed trimmed mesh be exported, saved, and loaded in third-party CAD system? Not currently. Although it is on our roadmap to do something like that, write parts of it to step, because it is just a it's a similar format to a traditional BREP based CAD object. Similar with Solver's results, is this saved on the trimmed mesh, or is it a separate file that can be exported, saved, and loaded by third party? I don't think we haven't done that, so I can't comment on that.
Yeah, we do our visualization. So currently, if you run a Flex job, we visualize in ParaView, which is a third-party open source visualization tool, and we output a tessellation for ParaView to render. That's an active. We've done work before to support Bezier cells to be able to render directly to Beziers. There will be some ongoing work to more natively support our trimmed representation in ParaView. But there is at least that kind of capability. So it's definitely something we're aware of.
Okay, let me just answer this one. This is actually about Qubit, not Flex. Can one import, I believe they meant export, the mesh from Qubit to ANSYS Fluent ready to go?
If the question is the Flex model, again, we don't support we don't support
yeah, I don't know. I don't know what exactly the user or the guest was intending here.
Yep.
The way that it reads is, can one import the mesh from Qubit to ANSYS Fluent? So if we're talking about Qubit proper as a traditional FEA tool,
yep,
processor tool, the answer is yes. If you're talking about Flex, the answer is no.
Correct. As you can see here, we have these export types. It's like the ANSYS CDB, CGNS, Fluent meshes, open foam meshes. So a lot of choices.
How do we choose the initial mesh size? Let's say we have square 1000 by 100 by 100 and a hole of radius 1. How to choose the mesh size? Well, currently we have two approaches. We have an approach where you can have one background grid per part, and then you can refine that down to capture the geometric features you're interested in. The other approach we have is what we would call a mesh cutting procedure, which essentially allows for a discontinuity in the background grid basis functions local to the hole, so that it behaves as it should, like there's actually a hole in the mesh. And then a third approach that's under development is just local adaptivity, where you'll be able to put more mesh right at where the hole is. That's probably going to be the preferred approach long term, but we haven't yet released that capability. Could you explain something about contact modeling technology of Coreform Flex comparing with the contact constraint approach? Okay, so I would say that we're building on what would be considered the state of the art in both mechanical contact literature or research in the more, like in the finite element community, but we also are bringing in a lot of technology from computer graphics, gaming in particular, in terms of the geometry processing to increase robustness. So I would say that while contact shares some similarities in terms of the response that you'll see in the actual bodies being modeled, it's quite a bit more modern than what you would find in traditional FEA. And I'm happy to explain that further offline. But that's about the best I can do, I think, right now. Okay. Isogeometric methods historically had some limitations when dealing with very large models, as IGA can become memory intensive. Is any of that relevant now? I think that there is, like I say, per degree of freedom. It's more expensive both in compute and memory. We have fully distributed capabilities and also have spent a lot of many years on this issue. And what I would say now is that we're not memory constrained, and we can scale to tens of millions of degrees of freedom without issue. So I think that there's a constant factor that you have to apply in terms of memory, a memory increase, but in terms of scalability and parallelism, there is no constraints that we're dealing with. And we've been able to do, very large assemblies of models without issue with our customers. Okay. Is there an integration with Moose plan? Good question. We do work with the Moose team closely. I don't think that we already have some integration capability. In fact, you can export directly to a format that Moose can now read in and perform isogeometric analysis in Moose. So I guess the answer to that is yes, we already have that. I
Yeah.
can't speak to whether it's released in Moose yet, but certainly we have people using it. Greg,
Yeah.
do you know?
And yeah, so we have capabilities released in Moose. It is still being actively worked on. What I'll also say is that I have a fork of Moose where I am updating the current IGA model, or one of the examples in the solid mechanics module, that does the C-frame problem. I'm currently working on that in my fork, and we hope to have that have a merge request up soon that demonstrates that capability.
Okay, that's the end of our questions. Thanks, everybody. We'll wrap it up here. We appreciate your time and attendance. Thanks.